Alright guys, mercifully this is the should be the last video, and in fact if I have anything to say about it, it will be the last video for GD&T 2020. Hopefully when a year rolls around we won't be doing it this way, but I've already gotten some comments back to you saying that the videos are beneficial, so I'm going to keep those and obviously make them available, but I still sort of miss the face-to-face classroom scenario. One benefit to this though is I can give it to you in digestible chunks as opposed to 2.5 hours of merciless classroom instruction. It's hard for anybody to bear up to that, including me. So great experiment here. I don't think I want to do this again soon, but we are at the end of it. And I always save this one for last for a couple of reasons. One is because of all the controls, runout is far and away the simplest. It's one of the most common callouts that you'll see when you're dealing with rotating equipment. Now, only certain industries deal with that, but it's not uncommon at all. And it has a benefit in that it's a relatively easy check for conformance to the drawing if you use a runout callout, because it uses fairly standard instruments. There are inspection devices that can support a runout as a specific callout, and in very many industries it's a critical way to make sure that things operate correctly. What I always like to start out with, because I always assume that you've been in your machine shop class and you all are familiar with the instruments that are necessary here. Now, unlike any of the other controls, this one assumes that you're going to use a specific instrument to verify the runout condition of certain features. That instrument, or those instruments, are a class of instruments called indicators. This is one class of indicators called a dial indicator. These come in different ranges of range. This is a half-inch range of indicator, and it indicates to the nearest thousandth of an inch. There are dial indicators that have much longer range, and there are dial indicators that have much higher precision. The highest precision dial indicator I have is 50 millionths of an inch. So they can be very sensitive, but a routine, this is a very typical dial indicator that you would see in a shop that measures only to 1,000th of an inch and only has a relatively small range. 1 inch is probably more common than ½ inch, but I have a 4-inch range indicator too. So they are a very useful and very adaptable instrument, and they are geared specifically to runout checks on parts. There's another class of instrument, also an indicator, has a totally different form factor. They operate differently, but the same thing applies. They have different precision levels. This is a 1,000th indicator. They also go down to at least a 10,000th of an inch. Those are fairly common. Anything beyond that you don't see too often in this form. The problem with these is nice and compact as they are, they have limited range. So in the instance of a dial indicator where I could have certainly an inch of travel, this one is, as the precision goes up, the range almost certainly goes down. So I only have about 30 thousandths of travel on this. I'm going to, at the end of this video, I'm going to go move the camera to a machine, and we'll set this up, and you'll kind of see how they work in reality, and be able to see how you can measure on the fly runout. If you look at the handout, and again I'll have scanned the handout and put it on canvas for you. It's a very, very brief chapter. It's 5 or 6 pages maybe. Mostly pictures, not a whole lot of verbiage, so you'll be able to see how it would be used, and these are all very practical applications. But what I think sometimes gets forgotten is what exactly are you measuring when you measure runout? We have two different symbols. We have a single arrow and sort of a double arrow. And this is runout of a circle. And this is total runout. And you saw this separation in some of the other controls. In profile, we have profile of a line, profile of a surface. This is an important distinction, and it's important here is that very often we are simply measuring a feature that is a two-dimensional feature. It's a boundary around something. And that's a two-dimensional check is this. And if we want to expand that to the third dimension and measure an entire surface or an entire boundary around something real and three-dimensional, we use total runout. And you saw that with this symbol too. I think you remember we had an all-around symbol and an all-over symbol with two circles. That's the same idea, is that an all-around is in one plane, and an all-over is just that, it's all over. So it's a three-dimensional boundary as opposed to a two-dimensional boundary. So we have the same concept here in runout. And I'll give you an example where you would use that and why it's important to have that additional symbol. But ultimately, let's stop and think about what runout is. Now if we look at a shaft here, I'll just draw it on the board so you can kind of see it's a shaft with a step in it. And the drawing shows this, which we now know as a center line, and in GD&T we don't call it a center line, we call it a derived median element, and that's what it is. But if you look at this, how many features do we have? Well, we have this diameter and this diameter. Now, if you look at the drawing, they look like the derived median elements are a single element, one center line. And in a perfect world, if everything were just perfectly so, they would share those two derived median elements. The center line of this and the center line of this would be completely coincident, and there would be effectively one line. That never happens in the real world. So you have to get the notion that when you make this shaft, you start out with a single bar, which is a single diameter, and a single center line or derived median element. Now again, we're always assuming that that derived median element is straight. If we need to keep it within a certain straightness, we have to make sure that there's a form control for straightness to do that. But in reality, when this gets made, I'm going to exaggerate this greatly, but in reality, there are two center lines here, and two features. And as much as the drawing shows one center line, there's really two. There's the large diameter center line and the small diameter center line a little bit here. Now, how much that distance is, it could be a very small amount. It could be a thousandth or less, and hopefully it is. But we do need to be able to measure that. We need to be able to measure the offset of these two derived median elements. So when you think about it in general GD&T terms, what we're talking about is a positional control. We're measuring the position of one derived median element versus the other. And as much as we want them to be one on top of the other, there'll always be a little bit of offset between them, and that's a translational problem. And runout is one way that we can check that very quickly, because if you think about it, if I take one of my indicators here and I hold on to this and rotate it, and I rotate about this center line, if this center line is offset at all, and I put my indicator on top of it, and I'll just draw that on, throw my indicator on. And let's say I zero that indicator right there. When I rotate the large shaft or the large diameter 180 degrees, where the center line of the small shaft was offset in the upward direction, let's say at the 12 o'clock position, that center line would then be rotated down 180 degrees, and it would now be at the 6 o'clock position. And that indicator would then move from its zero to some other location, and that measurement on the indicator would be the amount of offset from one location to the other. So if we take half of that value, that then becomes this, which is the offset amount of those two derived median elements. And it's really as simple as that. It's fast and easy to do. If you understand what you're measuring, you can come up with a very precise measurement of where the derived median elements are, one relative to the other. And honestly, it'd be hard to do it any other way. So in this instance, we're using an indicator to check a positional error, or check for positional error and how much there is of it. All right, so Runout does that sort of positional check. And it can also do a sort of orientation check. So in this case, we have a large shaft that we're going to call sort of our datum axis, and we're interested in the coincidence, or the line to lineness of the derived median element of this conical element. So again, if we separate that out, that conical element is a separate feature. It's got its own derived median element, and what we're looking to see is the derived median element of this conical piece. You know, we did this piece as a runout check. Now we want to see how consistent this conical feature is and its derived median element. This is where we make that distinction between circular runout and total runout. So if I put my indicator here, I guess I should touch that surface, and I put my indicator here and touch that surface. If I hold on to this part and rotate about that center line, if I run this indicator along this entire surface, I am doing a total runout check. And obviously, if I'm rotating about the derived median element or the center line of this shaft, if I run along that length, I should see no indicator movement. What if I do? What's happened? What has happened if I see indicator movement? Because it can't be that this one feature has two derived median elements. It can only have one, and we're rotating about it. So what that indicator would be telling me then is that there's something wrong with this surface. So if that surface is, instead of cylindrical, let's say it's slightly conical, or any weird scenario, anything that's going to cause that indicator to move will tell me that I have a form error of some sort. So we use the total indicator control and the ability to move the indicator along the surface of that part as a form check. What about here? What are we doing here? if I move this indicator along this surface, I can validate the form, the conical nature of that form, but that doesn't really tell me whether this center line is offset relative to this center line. So what I will use in this instance is a circular runout. So if I put my indicator here and hold on and leave it right there and rotate the main diameter, if this center line is offset, let me draw it in black. If that center line is offset, I will see the indicator move. And what I'm basically doing is checking through one circle. Instead of the entire three-dimensional form, I am checking one circular two-dimensional location to see if this derived median element is offset relative to this one. If I want to do it again, I can move the indicator here and check that circle and check that circle. So there's an infinity of circular checks that I can do on that form, and if you add them all up, then you've basically done a total runout. So that's really the difference. Is the circular runout is meant for checking a circular section of any shape, and ultimately anything that you can produce on a lathe will have a circular section. Even if you cut a shaft like that, and if you put an indicator and hold it right there and rotate about its center line, that will be a circular runout. And if you cut that bar in half right there, or slice through it, you'll see that that is a circular cross section. It has to be, because that's all a lathe can produce. Same thing here. It's just a different size circle, and there's an infinity of circles running down the length of this. So in this sense, we're almost checking the angularity. By doing a series of circular checks, we're checking the angularity of that surface. So runout is sort of an omnibus control that can check a lot of different things, but ultimately runout is only applicable if we can check it about a datum axis. We have to have a primary derived median element to establish as a datum, and if we rotate about that, then the indicator check will work. If we don't have a datum axis to check, then we'll be adding whatever sort of error is on this surface when we check this surface. That's sort of in a nutshell, the tolerance of runout. I don't want to go too much beyond this. I want you to actually read this handout. I think I told you in a previous video that this isn't going to be on the final or anything like that. You don't have to master it, but there's some very good illustrations in here. I want you to take a look at it, read it, and understand it. I think if you've taken the machine shop class, you've already done this somewhat. When you indicate a part into a chuck, so that it does not, the indicator does not move, that is a runout check. You are checking whether some portion of a part is running out relative to the derived median element of the lathe spindle. In that case, the center line of the lathe spindle is your datum axis, and you are checking to see whether that part is lined up with it perfectly, and the indicator will tell you that by motion. Once the indicator stops moving, you are coincident with the center line of the machine's axis or the machine's spindle. All right, that's it. I'm going to keep it that short. You can look at some of the other examples. If you look at the means this portion of it and read it carefully, study it, I think you'll be able to puzzle this out yourself. It is not complex, but it is common, and this is something that as machinists or inspectors you'll definitely want to understand. And I think the illustrations in the handout will go a long way towards helping you understand the difference between a circular runout, which is through one section, and total runout, which is along the axis of the machine. So there it is. That's in a nutshell GD&T. Seems like it's been a long time, but it's been done in bite-sized chunks. So again, I appreciate you guys sticking with me through this. The school does too. The schools, the universities, CVCC, all the junior colleges are struggling. They're having a hard time through all of this, just like we all are. It's going to have a big impact on their budgets, and you know, it can have a big impact on your futures. You guys have a plan for going to school and getting out, and part of that plan, I assume, was to get a real good job and make a lot of money. So we really wanted to go forward with this. We could have just as easily said, you know, everything's canceled, or you're going to get an incomplete if you were in the middle of a class. I'm glad that they were willing to allow us to do it this way, and they've really bent over backwards. There's a lot of legal consequences, financial consequences to shifting gears like this. Everybody's paid money for a certain thing, and I'm not sure they exactly got what they paid for, but I hope you're satisfied with what you got in this class. And again, the best way to make sure you're getting your money's worth is to communicate with me even after the final. Now, I told you that after the final, if you want to know your letter grade, I'll be glad to send it to you if you tell me who you are for sure. I do have to be a little bit careful about just randomly sending out letter grades or confidentiality rules about all of that. So again, thanks for toughing it out. I've learned a lot too about how to teach this class in a different way, and I'll take those lessons and take them into the next class. I will invite you, if for any reason you wanted to actually get another helping of this, is to pick it up next spring, and I think it'll mean more to you at that point. If not, thank you for coming. You guys are definitely on the right track. This is a good career move, I think, to get this technical education, because what I've learned here in this COVID business is not many of the technical people have lost their jobs or been laid off or sent home. We're all sort of working as we normally are, even harder. There's a constant need for stuff like this, and you can't really shut it off very easily. I think our government is learning that the hard way now. So again, thanks for attending, and hopefully I'll hear from you, or maybe even see you around campus in the fall.